Okay, Chapter 4, 2D conduction. We talked about how the temperature can vary as a function of, for instance, x and y in a plate like this. The left-hand side's at a temperature T1, the top, bottom, right-hand side temperature T2. We might be asked to find the temperature as a function of both x and y. Analytical way to do that is you write down the governing partial differential equation, there it is, the Laplace equation, with the correct boundary conditions, and then you solve that for temperature as a function of x and y. Generally a pretty difficult problem, pretty difficult. Even for simple geometries like that plate, it's the solution is pretty long. There's three ways that we can look at things like that. We can try and solve analytically the problem, which we don't do in ME 415. That's done in the graduate course typically. They spend some time on that. Number two, numerically, which we're going to do a little bit on and have our first computer problem on that, but it's done a lot in the graduate course because that's the way it's typically handled in the real world. And then we can talk about, we said last time, graphical type solutions, which aren't super accurate, but they do give you a feeling for the problem. So three ways to solve it: analytically, numerically, and graphically. We're going to do a little bit numerically on Friday, and we'll do the graphical this morning. Okay, so there's a set of rules for constructing a graph. We call that a heat flux plot. So the graph is called a heat flux plot. The plot is a plot of temperature lines and heat flow lines. The temperature lines are called isotherms. Adiabats are heat flow lines. Okay, so a heat flux plot is a plot that shows the isotherms and adiabats. What it does, there's a couple things it does. It gives an intuitive feel for the problem. Helps develop your engineering intuition, what you will expect. And the second thing it does is that it can give you an approximate heat flow or temperature distribution. There are a number of rules you follow as you construct this particular plot. I'll write them down here. So these are the basic rules. And I'll talk about these as we work a problem. Okay, so those are the rules that we have. And I'm going to give an example of that. Let's see, here it is. Construct a flux plot for this diagram. This is a plate. The plate, we'll assume it's square, make it simple. This could be, as a for instance, a copper plate, a 1/4 inch thick, okay. The top of the plate is at temperature T1. The right side's at a uniform temperature T2. Left side's at temperature T2. The bottom's at temperature T2. And we'll assume T1 is greater than T2, so T1 is hot, T2 is cold. And we want to, I'm going to make this a little bigger so I can sketch it better up here. Okay, rule 1, look for lines of geometric symmetry. This is a square in the middle, okay, vertically through the middle, 45-degree diagonal, 45-degree diagonal, that's geometric symmetry now, but now we have to check thermal symmetry. Take this one, fold it about, here it is, fold it about my arm. This side's T2, fold it up. No, not T2, T1. Not symmetrical, thermally. Fold it about a horizontal line through the center. When I fold this piece up, this temperature is not that temperature. Oh, over here, T2 here, fold it up, T2 here, yes. Over here, T2 here, fold it up, T2 here, yes. That answer is no. That is not a line of thermal symmetry. 45 degrees. T2 here, T1 here, won't work. Here, T2 here, T1 here, won't work. Vertical line, T2 here, T2 here, yes. T1 here, T1 here, yes. T2 here, T2 here, yes. Conclusion. The only line that has both thermal and geometric symmetry is a vertical line that goes through the center of the plate. There it is. Rule 2. If you find a line like that, that line is automatically the first heat flow line, called an adiabat. It pretty much makes common sense too, of course. That's the idea. Is if T1's 100 degrees and T2 is 0 degrees, guess which way heat flows? Straight down from the middle, from the top at 100 to the bottom at 0. Yeah, it makes common sense. Now, you can now try and draw the isotherms or the adiabats. I prefer to draw the adiabats because most people have some feeling for the way heat flows. Okay, I'll tell you an example. Start at somewhere else, not in the middle. Start up here. T1's 100, T2 is 0. Guess which way the heat flows? Yeah, you guessed it right. Heat flows from the hot surface 100 to the cold surface at 0. You've got to follow Rule 5. If an adiabat intersects an isothermal boundary, it does so at right angles. This is an adiabat, a heat flow line. When it comes into an isothermal boundary, it comes in at a right angle. Now, go ahead and fill the rest in. Okay. Leaves here, comes down, goes out there. Leaves here, comes down. Maybe that one will bisect the corner. Rule 6. If a heat flow line goes into an isothermal, it bisects that angle. Okay, 90-degree angle, 45, 45. Here. Here. These guys are isotherms. I'm sorry, adiabats. If you want to draw both sides, you can. You don't have to. Once you've found a symmetrical piece of the thing, you really just have to draw one part of this symmetrical piece. But I'm going to draw the whole thing so it looks like a complete diagram. Okay, down here. Up here like this. You don't have to go to the corner if you don't want to. It's up to you. You're in charge of drawing the diagram. If you don't want to go in the corner, you don't have to. Okay, there is a complete diagram of the heat flow lines. T1 is hot, T2 is cold. Now I'm going to draw the temperature lines. Start with the easy one first. If it helps you to put numbers, fictitious numbers, go ahead if it helps you. I'll pretend it's fictitious. This is 100, this is 0 degrees. Where do I think the line 90 degrees is going to be? Oh, I've got a really good idea. 90 degrees? I think it's really up here close. Yep, you're right, it is. There's one. 80. There's another one. 70, and so on and so on. I'm not going to draw all those, but I will draw. So these guys right here are isotherms. Rule 3. Everywhere in the interior, the adiabats and the isotherms must cross at right angles. Everywhere in the interior of the body, those guys have to cross at right angles. They're normal to each other, called orthogonal functions. And that's it. The heat flux plot is complete now. I've drawn the adiabats and the isotherms. Okay. Let's take another one. I'll take one that looks like this. I'm going to make it a little bit different here. Okay. This is a semicircle. Okay. The left and right hand sides are perfectly insulated. Both sides. The top is T1. The bottom is kept at constant temperature, T2. Construct the heat flux plot. And by the way, before I forget, let's go back to our previous problem. And I say, well, I assume T1 to be hot and T2 to be cold. I made a mistake. I want to plot the heat flux diagram if I assume that's the case. And I say, don't worry, it's the same picture. Don't worry, it doesn't matter which hot was cold. Same picture. So what you assume doesn't make any difference which one's hot, which one's cold. The picture is the same. It goes back to the PDE solution, boundary conditions. That's where it comes from, that conclusion. Okay, rule 1, lines of geometric symmetry. No. Folded above the bottom to the top doesn't correspond. No. The only one, yeah, you got it right here. That's a line of geometric symmetry. Thermal symmetry? No. Yes. Adiabatic, adiabatic. T1, T1, T2, T2. Yes, that guy right there. There he is. That is my first adiabat. If I assume T1 is higher than T2, then heat goes from the top vertically down to the cold surface, T2. And of course, it has to be at right angles. Now, heat that leaves the semicircle here, it has to leave at a right angle. That's the rule. Adiabats intersect isothermal boundaries at right angles. Yes, it comes out at a right angle. Well, of course, one comes out here, one comes out here, one comes out there. I'll make it symmetrical. You don't have to draw both, but I will. All right, he starts to go down to the cold surface. This is where the intuition comes in. He comes out of the hot surface. He wants to get down to the cold surface. He makes a rather sharp right turn. He can't get out the adiabatic boundary. Illegal. He can't cross the boundary there. Where does he go out? At the bottom, of course. Draw the next one. And the next one. We're going to stop there. Draw this one. And the next one. And the next one. There they are. These guys are the heat flow lines called adiabats. Now, that's where most people's intuition is. Now draw the constant temperature lines. Okay, let's start again and make some assumptions. I'll pretend that this guy is 0 degrees and that guy's 100, just to talk about something. Where do I think the 90-degree temperature line's going to be? Oh, okay. Let's take the easy one first, make it easy. The 10-degree temperature line. Here's a horizontal line, 0 degrees. 10 degrees, I think it's horizontal like that. Pretty close. Yep, I'm right. When I get to an adiabatic boundary, read the rule. Isotherms intersect adiabatic boundaries at right angles. When I get to this adiabatic boundary, the isotherm has to come in at a right angle. It has to cross everywhere inside the body at a right angle. Okay, the next one, and the next one, and the next one, and the next one, and this one. Everywhere inside the boundaries, these guys have to cross at right angles. When they touch the boundary at a right angle. Those guys are the isotherms. So now I've drawn the heat flux plot for that picture, showing you the adiabats and the isotherms. They start to bend upward. Matter of fact, in the limit, when you get to 100, there's the isotherm. It's a semicircle. Okay, we'll do one more. Let's see here, right about here. This is T1. This is T1. This is T2. This is adiabatic boundary. Okay, so draw the heat flux plot. Okay, let's take the easy one first. Let's say T1's hot, T2 is hot, T1's cold. T2's hot. I think he'll go out here and it'll make a left turn and go out there. Well, you know, yeah, that's what heat's going to do. Sure it will. Let's take another one down here at the bottom. T2 is hot, T1 is cold. Heat's going to come out of here. It comes out at a right angle. It wants to go to the cold surface. It goes along the bottom. It can't turn right because it can't get out here. Adiabatic surface, it can't get out. So it goes over here, and it goes out like that. Okay. Now I've got two heat flow lines drawn, adiabats. Try and draw the ones that make the most sense to you first. Then fill in the middle, the blank area. Okay, filling it. Comes out here, goes out there. Comes out here. Oh, I think it might bisect that corner. Rule 5. Yeah, isothermal corner. Comes out here, goes out there. Comes out here, goes out there. Yep, there they are. That's the heat flow lines. Of course, you can't have 3 different temperatures. In that case, this method doesn't work. It's got to be 2, only 2, T1, T2. All right, isotherms. The first one is T2, a vertical line, T2. The next one, if this is 100, T2, T1 is 0, you say, where's 95? Oh, I think it's close to 100. Right. Comes out here, goes down here. Rule 4. Isotherms intersect adiabatic boundaries at a right angle. There it is. And they cross everywhere inside at a right angle. There it is. Comes out here, goes over here, comes down here, goes out there. Comes out here, crosses here, there. Comes out here, crosses there, and goes there. That's the way these guys should all be right angles. There they are. Those are the isotherms. By making that sketch, it gives you an engineering intuitive feel for the heat transfer problem. Right there. You can sketch this on a napkin in a restaurant. You don't need your handheld. You don't need your smartphone. You don't need MATLAB. You don't need MathCAD. You don't need Excel. You can sketch what this thing should look like. And that's really valuable. Okay, how these lines change shape. Okay, I've got a couple more examples on a handout for you so you can look at it, because our book doesn't have many examples. And the rules aren't stated very well in the book, so I put the rules on the front page and 2 more examples on the back page for you. So now you've got 5 examples of these flux plots. Okay, so you can look at these for other examples. Okay. Now let's get to how do I get an approximate solution for heat flow and temperature distribution. All right, I'm going to talk about the first thing you do to do that is when you make your sketch, you try and make it so that you have what's called curvilinear squares in the body of the sketch. So curvilinear squares. I'll just draw a couple of things here and show you what they look like. Let's say that these are the adiabat lines. And this is the isotherm. So I'm taking out one of these things out of this picture right here. Let's see, I got 1, 2, 3, 4, 5, 6, okay. Now, a curvilinear square, of course, as the name says, it's a square with curved sides. A square with curved sides. The way you tell if you've got a curvilinear square is if you take the diagonals, and if the diagonals cross at a right angle, you've got a curvilinear square. It doesn't. Okay, take your eraser out and say, that didn't work very good. I'm going to move this line over to here. Oh yeah, that's pretty good. Now I've got a curvilinear square. So that's how they're defined, and then you construct this plot, try it. I'll try some simple ones. That's beautiful. I'll try one up here. Let's try that guy. Not bad. Could be a little bit different. I'll try one up here. Oh yeah, good one. This guy here? No, not close. This guy here, kind of surprisingly, not bad, not bad. Almost curvilinear square. Well, the handout that I gave you on the back side with the two other examples will show you how this person checked for curvilinear squares in the top picture. Check along there for curvilinear squares. Okay. And by the way, why are the heat flow lines called adiabats? Well, here's what happens. Here comes some heat, Q. It goes between these two lines. The same amount of Q comes out here. These lines called adiabats behave as if they were adiabatic. So the heat that comes in here can't cross those lines. So all the heat that comes in here goes out there. That's why these lines are called adiabats, because they behave as if they're an adiabatic boundary. Okay, so that's our heat flow. By the way, this thing right here is called a heat flow lane. Between my two hands is called a heat flow lane, L-A-N-E. After you make the sketch, as best you can do with curvilinear squares, M is the number of heat flow lanes. N is the number of equal temperature increments. L is going to be the thickness of the plate. And the way you get an approximate heat flow once you draw your diagram is M times L over N times K, T1 minus T2, T hot minus T cold. So if you make your heat flux plot with curvilinear squares, that's how you can get an approximate heat flow from hot to cold. Now, this wouldn't be very good. So what I would do is I'd get out my big fat eraser, I'd erase these two lines here. Those are pretty good up here. That's not bad down here. Look at this one right here. Wow, perfect. Perfect curvilinear square right there. Don't touch it. This one, no. I'd move this line down, this line up, and I'd put a line between them. It'll be better. If I don't like that, I take out my big fat eraser and erase it again and keep going until you get tired of erasing. It depends how much, how much time you want to spend. But the closer you can get to curvilinear squares, the better this number will be. you can't worry about the corner up here. You can't worry about it. You're not going to get curvilinear squares up there. You ignore it. You can't handle it. So you're going to miss the heat going from T1 to T2 right here. That probably is a small amount compared to the heat around the rest of the body. So yeah, it's approximate because I can't handle these two corners very well. I can't make curvilinear squares. Okay, the rest of it, how patient am I? How much time do I have? Well, that'll depend on my answer. Okay, so now got L defined, K is the thermal conductivity of the plate, and so on. So let me take this one here. Okay, M, the number of heat flow lanes, all right? Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12, it's M. Times the plate thickness. I don't know what it is, 1/4 of an inch copper plate, whatever it is, L is the thickness. Divided by N, the number of equal temperature increments. Here's what they are. The isotherms. How many increments are there with the isotherms? Count them. 1, 2, 3, 4, 5, 6. Times the thermal conductivity of the plate, K, times T hot. I'll just say, let's say it's 100 degrees, minus T cold, 40 degrees, 40 degrees, 40 degrees, 100 degrees, just some numbers. Put L and K in there, and voila, I have an approximate heat flow. I'm probably in the ballpark with the true answer. I might be off by 20%, I don't know, 25, 30% maybe. I don't care, I'm in the ballpark. Okay, now, that's the approximate heat flow. Now we do the temperature distribution. Here's how we play the game. We say, delta T, the equal temperature increments, you take T1 minus T2 divided by N. Okay. Hot temperature, 100, minus cold temperature, 40, divided by, count, what N is, we did. N was 6. So the equal temperature increments are 10 degrees. Okay. That means the line, the isotherm where my finger is 40 plus delta T, 40 plus 10. This line is 50 degrees. This line, I moved up 2 temperature increments, here and here. 50 minus 10, 40, not minus plus, 60, 70, 80, 90, and of course 100. There it is. There's the approximate temperature. Somebody says to me, I want to know the temperature in the exact center of the plate, right there. I'll say, about 66 degrees. About 66 degrees. Someone says, I want to know the temperature down here at that point. I'll say, about 55 degrees. About 55 degrees. Oh yeah. It gets you approximate temperature. Okay. How? By trying your best to draw curvilinear squares. The better your sketching skills, the more accurate your answer. No two people sketching this will probably get the same answer. Everybody's sketching skills are a little bit different, so there's not one magic answer. It depends on how much time you put in and how good you are at sketching with an eraser and pencil. But if you're doing a computer code and you have no idea what the heat flow is, and it spits an answer out for you, you could check that computer code with this real quick. And if the computer code spits out 10,000 and this thing here gives you 800, somebody's wrong. Either you're a really poor sketcher or there's something wrong with your computer code. So it's a ballpark kind of check on what the computer code spits out, which you might have no idea what the heat flow is in that problem. This would tell you if it's reasonable. If computer code spits out 10,000, this thing gives you 8,000, that's okay. I trust the computer code, because I'm not a very good sketcher. So that's what it does for you. It can be somewhat helpful. Besides the fact, you don't need to solve the governing partial differential equation. You don't need to solve that to say something intelligent about the picture. You want the isotherms? There they are. You want the way the heat flows? There it is, believe it or not. Believe it or not. So it helps you develop engineering intuitive feel for a thermal problem. Very, very valuable. Okay, now let's take a look at another way to solve these 2D problems with something called the conduction shape factor. That's given by the symbol capital S. Capital S. The conduction shape factor, the equations are in table 4.1. Let me explain to you first how you use them. Q equal conduction shape factor times the area times T, times K, pardon me, times K times T1 minus T2. All right, so that's how you find the heat transfer in the problem. If you want, you can call a resistance. It's 1 over SK. And so you could put it like this. And you can now add these guys to the previous resistances you had in problems. So you could modify the previous problems with this particular resistance, 1 over SK. Now we go to table 4.1 to get the values of S. Let's, I'll look at that and I'll put a couple up here for you. Let's see which ones I want to do. Oh, here they are. Okay, this is going to be a sphere buried in the ground. Temperature here is T2. The outside of the sphere is temperature T1. The sphere has a diameter of D. It's buried to the center line at a distance of Z. And of course, here's the ground. The value of the thermal conductivity is K. If the ground is sand, K of sand. If it's soil, K of soil. Back of the book, Appendix A, whatever it is. K, though, that K up here is the K not of the sphere, of what's surrounding the sphere. The problem in the book says, a sphere buried in a semi-infinite medium. Semi-infinite. That means the ground surface is here. Above here might be air. From my hand, which way does the ground go? Down. How far? It said semi-infinite. What's that mean? It means it goes down as far as you can go. The ground is down there. Okay. Above my hand, not ground, air. Okay. With that picture then, he says that the shape factor S, 2 pi d, divided by 1 minus d over 4z. You can only use that if z is greater than d over 2. That means the sphere has to be buried underground. It can't have part of the sphere outside the ground surface. It must be totally buried underground. What you do, you put that S, calculate it. First of all, check your condition. It's satisfied? Yes. If it's satisfied, here's the equation. Calculate capital S, put it up here, multiply by K of soil or sand, times hot temperature minus cold temperature, sphere temperature minus ground temperature. Q, how much heat's lost by that buried sphere. There's another one, buried vertical cylinder. By the way, somebody's done all the math work for you to get those conduction shape factors. The work's been done for you. It's pretty straightforward stuff. Go to table 4.1, look for your geometry, you got it. Okay, so here's the ground again. This time we're burying this cylinder, so here's the cylinder. The height of the cylinder is L. The diameter is D. K is of the ground. Capital S. 2 pi L. Natural log 4L over D. Only use this if L is much greater than D. The height much greater than the diameter. If you do that, there's S, there's that, and take that S, put it in here, multiply by K of the ground, T1 minus T2, you've got Q. So it's all pretty straightforward stuff. If you've got a problem that involves whatever, maybe convection here, convection from the ground to the air, you've got to add one more resistance, and that's convection resistance, 1 over HA. So you'd have this resistance for the sphere buried in the ground, plus a resistance for the convection from the ground to the air. Mm-hmm.
So these equations essentially allow you to solve 2D conduction without the differential equation?
Yeah, exactly. That's right. They're simple geometries. Yeah, exactly. Yeah. Oh, and just so you know, I'll tell you how many pictures are in there, because it's pretty complete. And these are things that we engineers look at quite frequently. So they're ones that occur quite frequently. There's one in there where there's 2 pipes buried like this, small, big diameter. This one's T hot, this one's T cold. How much heat's transferred from that pipeline to that pipeline? So maybe you're going to you're building a solar parabolic trough collector field up in the desert somewhere, and you're using oil on the collectors to capture the solar energy. So you've got a hot oil pipeline coming back from the field and a cold oil pipeline going out to the field. You don't dig 2 trenches, that's too costly. You dig 1 trench. And in that 1 trench you bury both pipes. And you might backfill it with sand if you're in the desert, or maybe soil. So now you've got a pipe carrying hot oil and a pipe carrying cold oil. Of course you want to know how much heat is being lost by the hot oil pipeline to the cold oil pipeline. It's in there. It's number 4 in that table. Number 4. So we find those typical conditions that we engineers see all the time with that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 guys. I've shown you 2. There's 15 total in that table. Okay, so a lot of conditions are in that table. And your homework has 2 problems involved using that table. Okay, now that takes us through the first half of chapter 4. We're going to do the second half on Friday, but I want to go through some things about the midterm now, and then we'll do homework. All right, Monday's midterm. Our next homework set is due on Monday, just so you know. The reason why I said to get it done by Friday, because you want to get it done by Friday. To ask me questions if you don't understand. Don't wait till Monday morning, it's too late. So try the homework. You got problems on the homework, ask me Friday. On Blackboard, there's a data package. The data package is what you're going to have in your hands during the exam that have table 4.1, not table 4, pardon me, just chapter 3. It's going to have table 3, 4, table Don't write these down because they're on Blackboard. Table 3.5, figure 319, figure 320, table, I think, 2.4, and other things. They'll have the Bessel functions, appendix B1, the K values, appendix A1, A2, A3, A4, for gases and air and water and so on, table A4 and A5. All that is in the data package. The data package is complete. It has stuff on radiation from chapter 13, stuff on convection from chapter 7. Doesn't make any difference. That's your data package for the 2 midterms and the final. You'll have it on Monday. When you turn your exam in, you turn your data package in with your name on it. I pass it back to you before the second midterm. You pass it back to me at the end of the second midterm. I pass it back to you on the final. You pass it back to me after the final. So you can mark it up. That's the point. You can mark it up. It's your data package. Your name's on it. Okay. That data package is on the Blackboard website tonight at midnight. Also on Blackboard, the first midterm from last year when I taught heat transfer. You'll see the problems I ask on the midterm. So I've got 2 first midterm exams with solutions on Blackboard tonight at midnight. What you want to do is you want to try and work them. Don't look at the answers. Try it. Give yourself 65 minutes. Put some pressure on yourself. Give yourself 65 minutes. See how far you can get. You've got the data package with Blackboard. You're ready to go. And when you're done, look at the solutions. Okay? That way you know the kind of problems I ask on the midterms. Because some people haven't had me before for fluids. So you'll know what kind of problems I ask. 4 problems on Monday. 4 problems. Oh, by the way, you can bring in 1 sheet of paper, both sides, 8.5 by 11, both sides, anything you want on there, any boxed equations I put on the Blackboard. You wanna photocopy all the homework problems on postage stamp size? Go ahead. Bring a good pair of eyeglasses. But you can put anything on there you want. Both sides of a sheet of paper, 8.5 by 11. Okay.
So the 8.5 by 11 is in addition to our data package?
You'll turn that into with the data package, though. Yeah. Okay. 4 problems. Roughly 15 minutes per problem. 65-minute class time. Roughly 15 minutes per problem. Don't fall in the trap of saying, "Oh, I'm a real bulldog. I don't let go once I bite into your ankle." No. At 20 minutes, go to the next problem. Try and maximize your partial credit. 20 minutes, move to the next problem. Don't keep saying, "I'm going to get this or else." Yeah, well, it's going to be or else probably. You don't want to get in that situation. Okay, so guess what? The exam covers chapters 1, 2, and 3. 1 problem from 1, 1 from 2, 1 from 3, and dealer's choice. I'm the dealer, okay? Dealer's choice. So 3 and 1. Okay, 4 problems. Okay, we'll talk more about it on Friday, but with those practice exams, I'm not going to do much reviewing. Your review will be try the practice exam, see how you do. That's what you want to do. And you've got the solution, so not a problem. All right, we passed back the homework today. I'm going to go through 2 things on homework that I found that I want to mention to you. First of all, don't do 1 problem. It involves more than I thought. Problem 3.142, it involves some derivation I don't want you to get involved in for the first midterm. So problem 3.142, knock it out of the course syllabus. There won't be anything like that as we talked about this morning. No, it's not a straightforward problem, and I really don't think it's going to be worth working. Okay, let's talk about 3.15. 3.15 is the wall problem. It has a hardwood siding on a house. It has hardwood studs, gypsum layer, and insulation. So this is a hardwood siding. The K value was 0.094 from the appendix. You had to go back to the appendix and find these guys. Hardwood stud. .16 gypsum. K for gypsum. .17 K of the insulation. 0.038. The reason why most people that had an answer slightly off from the correct answer was because they didn't have the right K values for the materials. And most of the errors were in that hardwood, because the word hardwood appears in there twice. But it's the second word that's important. Hardwood siding, hardwood studs. There is, in the appendix, something that says hardwood siding. There's also something in the appendix that says hardwood, just the word hardwood. The studs are then hardwood. They're not siding. A stud is not siding. It's hardwood. So you use the word hardwood for the studs and hardwood siding for the hardwood siding. Okay, so that accounts for some of the error that people were getting in the answers on that. Okay, any questions on that one then?
Why would those two be different if they're the same material?
Yeah, the siding, I'm not so sure. It's you know how siding looks on a house? You can put it on the outside of a house. I'm not sure it's actually not something maybe added to it or something, whatever you want to say it is. I don't think it's the same wood. They don't take it, they slice it, of course, but it is different. It might be the geometry, it might be the moisture content, I doubt that, but there's something that's slightly different, and it's not slight. It's 33% more for the stud than it is for the siding. So yeah, it's something different about it. That's an interesting question. It's not so apparent, okay? But sometimes I just wonder if the siding isn't been chopped up hardwood and then put back together again with a binder and some kind of adhesive, maybe. I don't know. Could be that. Okay, let's look at problem 351. Okay, this is the pipe which is carrying steam. It's insulated. Pipe, insulation. It's carrying steam. There's convection. T infinity. It's located in a large room whose walls are at T surroundings. I know the temperature on the outside surface, TS. He told me what it was. And he wants to know how thick the insulation should be. Thickness. What is T? Okay. This is the insulation. K insulation. This is K pipe. And the pipe. Okay, I guess that's all we need. Okay, we can then construct a thermal network from that with resistances. We'll start off with the hot side, T1. Our first resistance is the pipe resistance. Our second resistance is the insulation resistance. And then some of the heat leaves the outside of the insulation by convection. Going out to T infinity. By the way, this is T surface. That's T1. Some of the heat goes out by radiation to T surroundings. And we're going to call this Q1, we'll call this Q2, we'll call this Q3. And now we'll write the energy balance at the node TS. It says what comes into node TS must go out of node TS. Okay, steady state. No generation. Constant properties. Okay. I know T1. I know TS. I know T infinity. I know T surroundings. Okay. So I'm going to write Q1. Hot temperature minus cold temperature divided by the sum of the resistances between those 2 points. RP plus R insulation. That's equal to Q2, convection. TS minus T infinity divided by R convection. Plus radiation. I don't want to use a resistance for radiation. I can, I'll explain how in just a minute, but I don't want to. I know what radiation is. It's epsilon sigma A T S to the fourth minus T infinity to the fourth, or T surroundings to the fourth. Okay, put a check mark by everything I know. T1, TS, TS, T infinity, TS, T surroundings, got it. Epsilon given, A is a constant, area I know, pi dl. Yeah.
I don't know if you know area though, because without the T, you don't know.
Oh, on the outside. Yeah. The outside is unknown because T's unknown. Yeah. Okay, RP, I know it. R convection, I know it. Okay. RI, natural log R3 over R2 divided by 2 pi KL. Area here is pi d, so 2 pi R3 times L. I know K insulation. I know R2. What I don't know is R3. So solve for R3. Then the thickness of the insulation equal R3 minus R2. Okay, there it is right there. Okay, now, my point was, if you don't want to do it this way, then you can do it this way. You can use R radiation if you want. And if you do want to do it that way, then you get R radiation from chapter 1. I'll give you the equation number. Okay, there it is. R radiation. Equation 1.9. You can do it that way. It's just, in my mind, this was a little bit easier way to do it than... We haven't talked about the radiation resistance because we normally, it's not as convenient to use as convection resistance or conduction resistance. It's not as convenient to use. Why? Oh, it's got this fourth power in it, which makes it kind of messy. Okay, so any questions on the rest of that then? Okay, so that's how you do that guy right there. Okay, I think good stopping point. So we'll see you on Friday. If you